So now let's talk about finding intersections between lines and planes and between two planes. So first, let's talk about between lines and planes. Probably the easiest thing for you to do is to write out your line as a parametric equation, because then you have an equation that tells you what x, y, and z are, each in terms of one variable. You can plug those straight into your planes equation, and you're just left with one variable you have to solve for. So it's just straightforward algebra. So for example, let's look at x, y, z given by 3 plus 2t, negative 1 plus 3t, and negative 2 minus 2t. The plane x minus y plus z equal to 0. So all we have to do is take each of these components and plug them into here. X is 3 plus 2t, y is negative 1 plus 3t, and z is negative 2 minus 2t, that's equal to 0. And 3 plus 2t minus the quantity negative 1 plus 3t plus negative 2 minus 2t is equal to 0. Distributing here gives us 3 plus 2t plus 1 minus 3t minus 2 minus 2t equal to 0. 2t and minus 2t cancel, leaving us with negative 3t. 3 plus 1 is 4, minus 2 is equal to plus 2 is equal to 0. So solving gives us t is equal to 2/3. So well, we weren't looking for t, we're looking for the point of intersection. So instead, we'll plug t equal to 2/3 back into our parametric equation. So x is equal to 3 plus 2 times 2/3, which is 9/3 plus 4/3, which is 13/3. Y is equal to negative 1 plus 3 times 2/3, which is negative 1 plus 2, which is equal to 1. And z is equal to negative 2 minus 2 times 2/3. Negative 2 is equal to negative 6/3. This is minus another 4/3, so that's negative 10/3. And you can check that, okay, 13/3 minus 1, which is minus 3/3, plus negative 10/3 is equal to 0. So it satisfies that. Great. So here's question number 3. Let's find the points of intersection between the line given by x, y, z equal to 2 plus t, 3 minus t, and 4 plus t in the following two planes. First, the plane x plus 2y plus z equal to negative 12. And the other plane is x plus 2y plus z is equal to 12. And I would like to note that this is going to be a scenario where you don't have a single point of intersection. So go through the steps, see what happens, and then interpret your answer. What does it mean about the line L and each of these planes? Now let's talk about the ways that two planes can intersect. So if two planes are distinct, then the only possibilities are they intersect in a line or they are parallel. Now two planes are going to be parallel precisely when their normal vectors are parallel. That shouldn't be too crazy to see. More generally, this fact can generalize to saying that the angle, specifically the acute angle between two intersecting planes, is going to be the angle between the normal vectors. Let me note that even if the angle between two vectors is not acute, you can replace one of the vectors with its negative, and it'll still be normal to the plane, and its corresponding angle then will be acute. All right, so let's do an example of this, finding an intersection of two planes. So here are two planes, 3x plus 2y plus z equal to 0, and 3x plus 4y plus 5z plus 6 equal to 0. The first thing we're going to do is we're going to take the cross product of their corresponding normal vectors. This will actually serve two purposes. First, it will tell us whether they intersect or not. If the cross product is 0, then they're parallel, so the two planes must be parallel. Otherwise, if their cross product is non-zero, this vector right here we can actually take to be the direction vector for our line. So we can actually let this here be equal to what we've been calling v, because if the line that is the intersection between the two planes, since it lies on the planes, has to be perpendicular to both of these guys. And so there you go, you get a direction vector from this. So now we need to find any point that lies on both planes. This, what we can do here is we can note that so long as the coefficient, or the component, I suppose, of, say, I in the vector v is non-zero, then we can conclude that at some point x must be equal to 0 on this line because it's non-constant. When we parameterize it, this would contribute a non-trivial parameterization to x. We'd be able to adjust t so as to make x equal to 0. However, here I'm going to let z be equal to 0, y, I don't know, but still I can let z be equal to 0 because the component on k is non-zero too. So I'll say since the k component is not 0, we can set z equal to 0. We get 3x plus 2y equal to 0, and 3x plus 4y plus 6 is equal to 0. Let me subtract this top equation from the bottom one. Negative 3x and 3x cancel. 4y minus 2y gives me 2y, and 6 is just 6. So 2y plus 6 is equal to 0, which tells me y is equal to negative 3. Plugging this into, say, the top equation, I get 3x plus 2 times negative 3 is equal to 0, which you can figure out gives you that x is equal to 2. And so there we go. We have a point on the line, which is the point 2, negative 3, 0. And now that I have this, I can put together some symmetric equations, say. For example, I can write my answer as x minus 2 over 6 is equal to y plus 3 over negative 12, which is equal to z minus 0, which is just z over 6.